Welcome to the lecture on the implementation of the simplified DLX. So this is about implementation. What is our goal? Our goal is to design a circuit that can execute any DLX program that is stored in the memory, in the main memory. This circuit is called a stored program computer, and it is also known as a computer with a von Neumann architecture because it is based on von Neumann's paper from 1945. This is a practical computer that is based on Turing's idea of a universal Turing machine. The universal Turing machine is an abstract model. The stored program computer is a practical model. The first stored computers were built in the late 40s in England. Okay. The implementation consists of two parts. One is called the datapath, the other one is called the control. The control is a finite state machine, and the datapath is a circuit that contains registers and functional modules, most of which are combinational circuits, but not only combinational circuits. And these together constitute the datapath. I will elaborate on why this separation takes place. And the main reason is that it simplifies the task of designing the simplified DLX and of proving the correctness of the design. Now, one design principle that I will be using that takes a while to understand is that when we try to execute an instruction, a DLX instruction, this execution does not require one clock cycle, but in fact it requires many clock cycles. Okay? And there will be two main causes for the reason that this execution requires multiple clock cycles. The first reason is due to memory access, and I will elaborate on that one. I will just say that accessing the memory is very slow, and therefore it requires many clock cycles. And the second reason is we want to break the execution of a single instruction into small parts, small subtasks. And each of these small subtasks will, at least intuitively, but not necessarily always, require a single clock cycle. Okay? So we will see how the execution of an instruction is broken into lots of small, so to speak, instructions or subtasks, each of which takes a single clock cycle. Okay, so let's attempt to implement a DLX. We have our memory. The memory stores the program. This is a DLX program that we want to execute, and this is the data. The data consists both of input and output. So when I say data of a program, data of program is the combination of the input and the output of the program. Okay? Now, the control part, the controller, will consist of registers. These are just bunches of flip-flops, and in a combinational circuit. So this makes it into a finite state machine. And this finite state machine interacts with the memory. It can read and write words that are stored in the memory, and store them locally in its registers, and then use these values that it reads from the memory in order to perform some computation, maybe write it back into the memory. Okay? Now, the problem with this attempt, which I call the first attempt, is that when you study the number of states of a finite state machine, then the number of states is basically 2 to the power of the number of flip-flops. Now, in this DLX machine, we have lots of registers. We have 32 general purpose registers. We have the memory address register, the memory data register, the instruction register, the program counter. And so we will have too many states. Our goal is to design a controller that will have roughly 20 states. And by having few states, we make the task of proving the correctness of our design much easier, because the more states you have, the harder it is to argue about the correctness of the finite state machine. Now, before we elaborate on how one can simplify the task of designing the finite state machine that is the control, we need to talk a little bit about the interface with the memory. So I want to introduce another controller. This is not the controller of the DLX. This is the memory controller. And this controller is in charge of the interface between the CPU, or the computer, and the memory. Okay, so we will have our controller of the DLX, and we will have the memory. And in between, we will have the memory controller. And all interaction between the DLX and the memory takes place through the memory controller. Okay, so now we have to explain why we need this extra controller in the middle. So let's talk about the external memory for a minute, the main memory or external memory, as opposed to the local memory of the DLX, which is the registers, right? We have registers over here. So there's this type of memory and there's this type of memory, and they're not the same at all. Good. So the executed program and the data are stored here in the memory. And the memory controller is a circuit that is positioned between the DLX and the main memory. This is just another finite state machine, and it has inputs and outputs to here, inputs and outputs to the memory. And the main problem that the memory controller is trying to help us solve is that the memory is unpredictable. It's unpredictable in the sense that we do not know in advance how many clock cycles are required to complete a read or a write to the memory. Okay, so there is some uncertainty about the number of clock cycles that are required to perform a read or a write to the memory. Now, when we think about a register that is like a general purpose register, or maybe your PC or IR, whatnot, then accessing this register takes a single clock cycle. However, reading or writing in the main memory typically takes many clock cycles. Why is that? Well, it has to do with the way that the memory is organized. Okay, so we have a thing called the memory hierarchy, in which the memory, in fact, is built out of different layers called L0, L1, L2, and so on. And then we may have our main memory. And below that, we might have even the external memory, which is like a disk. Now, when we try to access an element, we access it from here. And if it doesn't reside in L0, we go to L1. If it doesn't reside in L1, we go to L2, and so on. And we don't know in advance where the element will appear, the data item that we want to read, where it will appear. And therefore, that is one reason for the fact that we cannot anticipate in advance how many clock cycles are required to access the memory. Now, because we do not know how many clock cycles are required to complete the memory access, we will introduce a special signal called the busy signal. And the busy signal is a signal that the memory gives to whoever is accessing it and tells it, I'm still busy with the memory access that you just asked me to do. And it is the output of the memory controller as well. And it tells the DLX whether the memory is still executing the previous memory access or not. Okay, so let's go back to the diagram we had over here. We will have some busy signal which is sent from the memory and is forwarded by the memory controller to the DLX controller. And as long as the busy signal is high, is 1, is valid, then the DLX knows that the previous memory access has not been completed yet, and it still has to wait. And once the memory access is complete, the busy signal goes down, say to 0, and then the DLX controller knows that the memory access has been completed. Okay. Now, the DLX may issue a new memory access only if the busy signal is low, namely if the previous memory access has been completed. Okay, so let's talk about what the memory controller looks like. So this is our memory controller. Of course, it's a synchronous circuit, so it has a clock input. It receives 2 inputs. This comes from the DLX. The DLX sends a request either to perform a read or a write. It also sends the address that it wants to access, and if it wants to perform a write into the memory, then it needs to send the data, and the data is sent from here, from this port, the input. Now, the memory controller informs the DLX whether it's still busy with the previous memory access, and if you're performing a read, the outcome of accessing the memory is sent to the DLX through this output port. Okay, so we have our address, our input, and our output, and we will connect certain buses, which I will elaborate about later, in the DLX to these input ports or output ports of the memory controller. So the memory controller is a synchronous circuit, and its specification is as follows. It has an input, the inputs which are in 32 bits, address 32 bits, single bits of memory read and memory write, and of course the clock signal. The output consists of 32 bits of out and a busy signal. Now, you're allowed to change the input only if the busy signal is low, because otherwise the memory is still busy with the previous memory access and you may not change the inputs. Now, if the busy signal is 0 and previously, in the previous clock cycle, it was 1, this means that we just completed a memory access, and then it depends on what we were trying to do. If we were trying to do a read, then the output will give us the word that is stored in the memory, in the entry of the memory that is addressed by address. And if we're trying to do a write, then we know that now the memory stores in address what we asked it to store. Okay, so this is the memory controller and the way it helps us interact with the memory. Okay, so now that we have the memory controller, we have the finite state machine of the DLX, we have the main memory of the DLX, and in between we have our memory controller. And as you can imagine, we have in a communication between the DLX controller or the DLX and the memory controller, and we have communication between the memory and the memory controller. Okay? Good. So now we have a simplified FSM. It's broken into 3 parts. Now let's look what happens here inside. Here inside, in order to simplify the finite state machine, we partition it into 3 parts. A small controller, combinational circuitry, and the registers. Okay? And so this fellow is also a finite state machine. We have two finite state machines here, the memory over here. And this finite state machine we partition into three parts: the controller, combinational circuits, and the registers of the DLX. Okay, let's try to understand how information flows in such an architecture. So let's start with the communication between the memory and the DLX. We have two parts, the one to the registers and the one with the controller of the DLX. So the first one, between the registers and the memory controller, well, this is the MAR and PC, or the data, the MDR and IR, which are used in load, store instructions, and instruction fetch. So in a load instruction, you have your memory address register over here, sent in as an address to the memory controller, and you have a read request that comes from the controller to the memory controller. This memory controller issues the request to the memory, and then eventually the memory responds with the response, and the value is sent to the MDR, stored over here, after the busy signal goes down from 1 to 0. Okay? If you're trying to do a store, then you have your two registers, the MAR and the MDR, and the controller issues a write request. The memory controller forwards this request with the address given to it by the MAR and the data given to it by the MDR. So the in will equal the MDR. And now the data that is sent to the memory is stored in the address that is specified by the MAR. Now we have another access to memory, which doesn't relate to data, but it relates to the program. We want to read the next instruction. The next instruction, its address is stored in the PC register. So we issue a read command to the memory controller with the address given by the PC. We send that to the memory. The memory responds, and it gives us back the instruction. The instruction now is stored in the IR, and now we can start executing the new instruction. So we have load, store, and instruction fetch. Okay. The controller, as I emphasized in these three cases, sends the memory controller either a read request or a write request, or none of the two, in which case I will call it idle. This might be the case in which the DLX is busy processing things inside and it doesn't need to access the memory. The memory controller sends to the controller the busy signal, telling it, I am still busy with the previous memory access. Good. Let's talk about the signals that go between the controller and the registers. The controller sends to the registers mainly clock-enabled signals. These are signals that tell the registers that they should sample their inputs and store the value of their inputs that they receive through their inputs in the register. The registers, on the other hand, send to the controller, for example, the opcode of the instruction. So the IR, the instruction register, sends to the controller the opcode of the instruction. Also, if it's in R-type, you also need to send the function. Okay, there are two fields in which the encoding of the thing that now needs to be executed appears in the instruction itself. And so these fields are sent to the controller so that it knows what is the current instruction. The third part is the communication between the combinational circuitry and the controller of the DLX. The controller tells the combinational circuit what operation it should perform. For example, if you have an ALU, this is an arithmetic logic unit that may consist, say, of an adder subtractor, then you want to tell the adder subtractor whether it should do an addition or a subtraction or a bitwise or whatnot. And the combinational circuit tells the controller some information. For example, it would tell it whether a result of some computation was 0. We'll call this result A. So it tells us whether A is 0, and this is necessary for the controller to decide whether a branch is taken or not taken. So this we need, for example, in the execution of branch equals 0, branch not equals 0 instructions. Finally, we have the communication between the registers and the combinational circuitry. The registers send to the combinational circuitry the arguments. For example, if I want to do Rj gets the value of Ri1 plus Ri2, I need to send the two contents of these registers to the combinational circuit, which performs the addition. And then the combinational circuit sends the result back to the registers, which store it in Rj. Another example is when you want to increment the PC, the program counter. So one of the registers is the PC, you send it to the adder increments it by 1, sends the result back to the PC, and now the PC has been incremented. Okay. So let's recall, what are the registers in the DLX? They're all 32-bit wide, and we have 32 general purpose registers called R0 to R31. We have the instruction register that stores the current instruction that we are executing. This instruction register is surrounded by some additional circuits that help decode the current instruction. We have the program counter that holds the address of the current instruction, the memory address register that stores the address that we want to access in the main memory in order to read data, and the memory data register, which stores the word that we want to store in the data part of the memory. In addition to that, we will introduce 3 more registers for the implementation of the DLX. We'll see them in a minute, A, B, and C, which are all clock-enabled parallel load registers. Each of these registers has a distinct clock-enabled signal that is computed by the finite state machine, the controller of the DLX. And we refer to these clock-enabled signals as follows. The clock-enable of the PC is called PCCE. The clock-enable of the MAR is called MARCE. The clock-enable of A is AC, and so on. Okay. So we understand what the registers are. We understand how we partition things and how we partition this part, this finite state machine, into 3 parts in the hope that this controller will be simple. Now, one problem that we notice immediately is that we have a problem in managing the general purpose registers R0 to R31. We have here many registers, and it's kind of cumbersome to control them using this controller. So in fact, what we would like to do is we would like to encapsulate the GPRs in a separate module to simplify things. And in fact, what we will do, we will see this later, we will use a module called a dual port RAM to implement the GPRs. So before we worry about how the GPR is actually implemented, how these 32 registers are implemented, let's describe an interface which simplifies interaction with the GPR. In this interface, what we have is we surround the GPR with 3 registers, A, B, and C. A and B are contain the 2 contents of the registers that are stored in what is called RS1, RS2, or RI1, RI2 inside the instruction. So in the instruction register has fields which tell us what is the first argument, the second argument, and the destination. Each of these are encoded using 5 bits. So there are indices between 0 and 31. And the GPR, you may ask it to perform a read. You want to take the 2 indices I1 and I2, and you want to copy the contents of RI1 to A and the contents of RI2 to B, put them over here, and then you could use them in the next clock cycle. Another option is that you have computed some result, you stored it in C, and now you want to copy the contents of C to your destination register RJ. So the IR sends these 3 fields to the GPR. The controller tells the GPR whether it wants to perform a read or a write, and it sends clock enable signals to the 3 registers A, B, and C so that they know whether they should sample their inputs because a read is taking place or a write is taking place. Okay. Now, the important thing to understand in this context is that our controller ignores details, and therefore it has fewer states. So our controller does not really care what the values of I1 and I2 are. It just knows that now it needs to perform some kind of read according to what appears in the instruction. It doesn't care what the destination register is. It just knows that now it's supposed to do a write. So the controller has a very high view of what is happening. It doesn't have a detailed view, and as a result, because it doesn't have a detailed view, the number of states of the controller is reduced, which is our goal, to simplify the controller. Okay, so let's give here a sketch of how we could design the finite state machine which controls the whole DLX. So we have a small controller. We have combinational circuitry, which may consist of our ALU and our shifter. We have our GPR, here it is, and it is surrounded by the registers A, B, and C. We have 4 more registers, the MAR, MDR, PC, and IR, which are connected to the memory controller, which is connected to the main memory. Okay, now let's look at how the controller interacts with our DLX. Okay, so to the memory controller, we already know it sends read or write signals, and it receives from the memory control the busy signal. It sends clock-enable signals to the 4 registers over here, and it gets from the IR the current operation that needs to take place. These are encoded in the fields which are called the opcode and the function. The controller also sends clock-enable signals to A, B, and C over here, and it also tells the GPR whether it should do a read or a write, and the GPR tells the controller whether A equals 0. This we need recall for the branch instructions. The controller also tells the combinational circuitry whether it should perform, say, an addition or bitwise or whatnot, or a shift. The result of the combinational circuit, the output of the combinational circuit, is sent perhaps to C to be stored in a destination register in the GPR. It may be sent to the MAR, MDR, or PC, because if it computed an address, you need to store the address over here. If it computed a data that you want to store in the memory, then you need to store it over here. Or you may have performed a jump, and therefore you have a new value for the PC, or just incremented the PC. You need to send the output of the combinational circuit to the PC. Okay? So this is a very sketchy description of the DLX design, and we have a lot left to see. We have to see lots of details, and one thing that we want to see is how this controller, in fact, can be implemented by a finite state machine with at most 20 states. Okay. In this figure, we see a more detailed description of what is called the data path. So here I'm not giving any details about this part, about the controller of the DLX, or the signals that the controller receives or sends to the other parts of the design. We just see here the registers A, B, and C, the general purpose registers, which reside over here, the MDR, which resides over here, the IR that hides here inside this box, the PC that hides here inside this box, the MAR that hides over here. Okay, these are the registered parts. We have our ALU, which performs addition and subtraction and bitwise operations. We have our shifter, and in addition to that, we have lots of muxes, multiplexers, and these multiplexers are of course controlled by the outputs of the controller, and they determine how signals propagate throughout this circuit. So let's explain how the controller can control such a data path. Whoops, sorry. Okay. For the purpose of explaining how the control controls the behavior of the data path, let me introduce an idea called register transfer language, RTL in short. So, register transfer language is a language that describes how the control governs the behavior of the data path. Okay? So, we know that the mechanism for controlling the data path is through these red signals, the clock enable signals and the operation which is fed into the ALU, whatnot. We know this, okay? But how do these, what is the effect of these control signals, okay? So the simplest control signal is, of course, the clock enable signal of a register in the data path. So the control sends a clock enable signal to one of the registers and tells it, please sample the value at the input and store it. Okay. So this means that in each state of the finite state machine, which implements the control of the DLX, the control tells which registers should update their values, read whatever is in their input, and use that value from that point on. We specify the action that the controller tells the registers to do by the register transfer language. Okay, so the register transfer language actually tells us how information moves from between different registers in the data path. The operands of the RTL instruction are the data path registers, and the calculations are performed by the combinational circuits in the data path. And every DLX instruction is executed by a specific sequence of RTL instructions, and most RTL instructions, except those that access the memory, require a single clock cycle. So here's an example of how we can control the data path. So we see here just a segment of the whole data path, just to try to get an idea of how things work. So here's register A, here's register B. Here we have a bunch of muxes. We have here the adder. We see that the adder feeds back A and B. We're not depicting everything yet. There are lots of control signals over here, so we'll depict them in a second. I just want to emphasize that this input is a constant input. It is 1. It encodes the number 1 in binary, and this input encodes the binary 0, the number 0 in binary. Okay, now let's show the control signals. So we have clock enables for the two registers, and we have select signals for the muxes. We use the same select signal for this mux and this mux. Here we have S2, here we have S3, and these are all our control signals that we are focusing on for this example. Now let's assume that we want to execute the RTL instruction, that is A gets the value of A plus B. So what do we want to do? We want to take the value of A and somehow feed it into the adder. We want to take the value of B and also feed it into the adder. And then we want to take the sum and store it in A. Okay, so let's try to understand how we could go about such an addition. Okay, so one way to go about this is as follows. We will send A like this to the adder. We will send B like this to the adder. And then the outcome of the adder is sent to here and goes into A. Good. Suppose that this is the way we want to implement A gets the value of A plus B. All of this takes place in one clock cycle. So S1 needs to be 0. So we set here S1 to be 0. S3 has to be 0 as well. S2 has to be 0. A has to sample its input, so it gets a clock enable of 1. B is not supposed to change its value, so we give it a clock enable of 0. I just want to remark that one could also implement the same instruction a little bit differently by routing A along this path and B along this path. Okay, so there are two ways to route A and B into the inputs of the adder. Addition is commutative, so it doesn't matter if we do A plus B or B plus A, it will give us the same result. Okay, but let's stick to the yellow implementation for simplicity. Okay, let's see another example. In this example, we want to compute the RTL, which says A gets the value of A plus 1. Okay, so where's the 1? We're looking for a 1. We must have a 1. Okay, so the 1 is over here, so this means we need to route this thing into the adder. And now the A doesn't have an option, it has to go through here like this into the adder, and the adder will send its value to A. Now we can determine the values of the control signals. S1 has to be 1, so that this input is fed through. This is a 1. S2 has to be 0. S3 has to be 1. A has to have a clock enable, and B must not have a clock enable. So if the control sends these control signals, then the effect of sending these control signals will be the execution of the RTL instruction. A gets the value of A plus 1. And it's important that this A refers to the value in the current clock cycle, and this A refers to the value of A in the next clock cycle. Now, how would we execute the RTL, which is A gets the value of A plus B plus 1? Well, we can't add 3 numbers in one clock cycle. The adder has only 2 inputs. So how do we do that? Okay, I'll leave it as a riddle. Now let's consider the RTL instruction B gets the value of A. What does that mean? How do we copy the contents of B into A? There's no direct path from the output of B to the input of A, right? So here we'll have to employ some trick. And the trick is as follows. We will say, well, A is the same as A plus 0, right? So now we want to add A plus 0 and store the result of the addition in B. Okay, so that means that the B has to be, the 0, has to be sent from here. And A now doesn't have an alternative. It has to go like this. And now the outcome of the adder should be stored in B. So now we can determine the values of the control signals. S1 has to be 0. S2 has to be 1. S3 has to be 1. The clock enable of A is 0. The clock enable of B is 1. Very nice. So we were able to copy the contents of A to register B. How about copying the value of B to register A? Can you think of a way of doing that? I'll leave that as a question. Good. So to summarize, what we see is that we propose the following data path for the DLX. What is missing in this diagram, and this is important that you understand that it is missing is the controller. All the signals that are sent between the controller and the data path, they're not depicted, okay? So this is missing, okay? What do we see here? We see here the memory controller, how it interacts with the data path. We see here again the memory controller. So the memory controller gets the address from here, it gets the data from here, and it gives the data from here. Okay, this is the connections that we have between the memory controller and the data path. Recall, we have another connection to the controller, the DLX controller. Between the DLX controller and the controller, we have the busy signal. So I'm just putting it here to make sure that you understand that this is missing, the busy. And we have the read, and we have the write, which is sent from the controller, the DLX controller, to the memory controller. Okay, this is missing. All the clock enable signals are missing here. Each and every register must have a clock enable. Also here we will have a clock enable for the PC, a clock enable for the IO. Okay, we are not depicting the select signals. Okay, so there's a mux over here. This mux needs to select either the left input or the right input, and these inputs are determined. Which input to select as the output is determined by the select input over here, which is sent by the controller. Okay, it's an output of the controller to this mux, and the other muxes as well receive such select signals. This completes the first part of the implementation of the DLX. Thank you.